Anyway, I got an email from Nichols just now that said he couldn't come today. So sorry about that. But anyway, he's coming on Wednesday, apparently. Like, I guess I didn't remind him yesterday or something. I don't know. So he's probably got a lot of stuff going on and forgot about it. But felt pretty guilty, which is good. Use that against him. So anyway, so I'm just gonna lecture on some stuff today. So sorry about that. I mean, anyway, just heard it like 5 minutes ago. He sent an email. So I guess he had a calendar notice. Yeah.
Sorry, you still need to submit a picture.
Yeah, you can get the 20 points, whatever. And I'll put another one for Wednesday, the same thing. Yeah, so since I said you'd get that, like it's just fair to do that, I think, That can be a question too. So, yeah, so there you go. 2 for 1. Let's see. So I wanted to go through, I got a couple questions on this E part of this thing and whatever. So it sounds pretty mystical, whatever he says here. So he says reversible dynamics are therefore spatially confined to long-lived portions of the sample, incredible strain, and this couple people asked, so I had to kind of figure out what's going on. So anyway, so thought I'd just mention that. Here, so so he's got this is the last thing. Let's see. So he shows this thing. Well, he's got and the point that he mentions in the text is that the red circles are above the red squares and the blue circles are above the blue squares when you're at the high strain amplitude, which is where it's a liquid. Right. So he says, so this blurb that he says indicates that like XPCS is looking at kind of at like whatever Q. So it's looking at something like 100 angstrom size scale. And then the rheology measurement's looking at a bulk sample on centimeters. So the bulk sample is showing more relaxation, so lower correlation. This is a measure of the correlation, so it's less correlated than the XPCS measurement. And both when he averages over 2 and 4 cycles. So that mouse like that there. So he's talking about wherever the first picture is somewhere. He shows all the cycles from it. Yes, so he's talking about like he's got the cross diagonal where T1 equals T2, then the thing repeats. So most of the pictures only go up to, so the repeat period is like half T by 2, and T is the cycle of the oscillation, capital T by 2. So he's got like one oscillation, every 2 would be like one oscillation. So he's got like four of these 6-second oscillations going through this thing. Right, each oscillation is 6 seconds. It turns that way and then back, right, like a sine wave. So anyway, so when it's 2, he's averaging 2 of them, and when it's 4, he's averaging 4 of them. So he gets different result when he averages different numbers of them, and that changes. That's what he has 2 and 4 here. So it's, I guess with 4, it's like lower, you lose the correlations when you go average 4 instead of 2 cycles. I'm not sure exactly why, but that's how it works. So anyway, but his main point in that blurb is that the XPCS is looking at a local level, so it's seeing somehow like more highly correlated things. And then and then the other one's an average over the entire sample, and it's seeing less correlation. So he's saying that there's like regions of correlation. It's not homogeneous. There's regions with high correlation, XPCSs, and then the average is lower because it's also mixed in these lower correlation things, so that was kind of weird. That was like a flyby. Is he in the class? I don't even know. Yeah.
Just for us,
Say it again.
Does the rheologic curve and the XPS curve, do they should be correlated all the time or?
They should be the same, I guess. If it's a homogeneous system, they should give the same number. But they give a different number. And then he says the reason that they're given different numbers is because XPCS looks at a small scale. So it's seeing just one spot with with higher correlation. And then the other one's averaging over the whole thing. I guess it depends. Whenever someone says average, it depends what kind of average it is. Like, is it a mean or is it a harmonic average, or because the result will be different, right? Like we learned that with RG and RH. So the matter is which average and also which moment of the distribution you're looking at. If it's a arithmetic average, like it could be the second moment, third moment, whatever. So like the thing squared, the thing cubed, whatever. So anyway, so that will matter with what value you get for the averaging that occurs in the rheology. That's not clear which average it is. I guess it's kind of the hydrodynamic average to be the harmonic. So the small things would weigh more than the big things. I guess I could tell you why it's lower than the other one. Anyway, it's a little so in that context, maybe you can understand what he said here. It's at the bottom. The reversible dynamics are therefore spatially confined to long-lived portions of the sample, and the recoverable strain in the nonlinear region is manifestation of the constrained positional fluctuations of the fumed silica particles. So the constrained within domains somehow where the correlations are higher, and the correlations higher because they're constrained in a domain. But when he looks on the average over the rheology, that washes out somehow. It's a lot of words that, you know, it's kind of hard to say it, I guess, but and then if you don't really read the thing, you won't know. Anyway, the idea is to go back and try to read it and figure out what he was saying. And at first I didn't have any idea what he was saying, but I think that's more or less the story. Like he's comparing the two techniques there. He's trying to get an idea of the homogeneity of it. I'm not sure there's another way to do that, like to say, is it homogeneous or not? I guess, anyway, it's kind of hard. Maybe there's ways to do it. Like you could do spot probes and see if you get different numbers for different places, maybe. But anyway, that's that thing. That was Ian. People gave like 2 or 3 people emailed me. I told them what I just said to you. But I thought maybe it was worth repeating because I said before I didn't know what he was talking about. So it's kind of, that's more or less what I get from it at this point. But anything else on that, on the homework, or I guess it was okay. All right. So let's see. Let me go. All right, so I want to go, I guess, back here. Oh, so you guys that came in late, Nichols didn't make it. He like canceled at the last minute. So but he's going to be here on Wednesday. So you can still get the 20 points if you do a selfie for today, and I'll do another one for Wednesday to try to get turnout for that. But sorry about that. But it was kind of like, I think he just forgot about it. And I should have reminded him yesterday, but I was kind of doing other stuff. I think I reminded him though on Friday, so it's kind of weird. Let's see. So we're at it's 2 from this guy. And then I want to do this thing too. So let me get these guys down. All right, so I gotta show you something. Slide 56. So full base 56 here. So yeah, so I wanted to maybe there's just a couple slides on what this is kind of what Nichols is going to talk about. But it's a little bit of an overview, and the homework this week's going to be on this for sure. So that's the wrong one. Sorry. All right, this one, 56, there. All right, so before, anyway, last time I talked about we were talking about DLS, and I said you could do this microreology measurements by putting probe particles into the material and doing kind of DLS on the probe particles, then do a conversion to get the loss and storage modulus, which is kind of interesting. That could be a homework too, but it isn't. So anyway, so this thing, it turns out so neutrons are generally much more less used than X-rays, because X-rays are really easy. Like you can have a lab X-ray source. You can do X-ray diffraction and X-ray scattering in your lab. And the synchrotron is like 100,000 times the flux of the lab. So you can do things that would take 2 hours in your lab in less than a second at a synchrotron. So you can do a higher throughput, and you also look at dynamics for the synchrotron, right? So that's like great. So neutrons, on the other hand, first of all, you have to have a nuclear reactor, so usually you need a nuclear reactor, and you poke a hole in the side of it and neutrons come out. Then you put those through like water to cool down because when they come out of a nuclear reactor, they're really hot and there's a broad spectrum. You want to get broad spectrum of energy, which converts to wavelength. So there's particles like 1/2 mv squared. So the velocity is going to go, the energy that comes out of the nuclear reactor, it's going to have a broad spectrum. It's like a nuclear bomb going off, basically. So it's not a single event exactly. So you want to narrow that down, because when you want to do a scattering experiment or some other experiment, you need to have like monochromatic collimated. Collimated means it's going in a straight line. Monochromatic means one wavelength, one energy, and then coherent is usually pretty nice too. Like a laser means all the waves are in phase with each other. So nuclear bomb, coherent is kind of out of the question. Coherent you can get. All right, so the sun is kind of a hydrogen bomb, and the light coming off it is perfectly coherent when it reaches Earth, because all the radiation that was incoherent destroyed itself. Like things that had a peak and a valley together, by the time they reach Earth, and starlight too is perfectly coherent, because by the time it reaches here, anything incoherent has already been destroyed. So it's only coherent that shows up. So coherent is kind of out of the game with neutrons. So you're not going to be able to do dynamic light scattering with neutrons, because you need coherency in order to have this kind of speckle pattern show up. Okay, so lasers can do it, and a synchrotron can do it, because in a synchrotron, every time the charged particles in a ring, every time it turns a corner, there's an energy involved in magnets making it turn the corner. Energy is converted into X-rays when it comes out. So basically, you're converting the kind of the turning thing of the energy into electromagnetic pulse coming out. It's like Maxwell's law. So the direction kind of goes with the field that you put on, and the current, the magnetic field you put on, and the electric field you get out of it goes with like your right hand rule thing, like the direction of either one, and then you get the direction of the other with your thumb, right? So anyway, so that's what's happening in a synchrotron. You're changing you have a charged particle going around, so there's a field, there's a current that's going on. There's a magnetic field you put on it, so you get an electric field out of it when it turns a corner. An electric field, once you get a pulse in electric field, there's a corresponding magnetic field that's kind of out of phase with it that's created also. So the two go together. And that's how once you make the pulse of an electric field, you get a pulse of magnetic, and then they resonate, and that's the electromagnetic wave that comes off, right? And the energy of it. So you can tune the energy to whatever you want, but basically, if you get the energy at 10 kilo electron volts, which is kind of a lot, basically you get X-rays out of it, right? So that's basically the synchrotron. And because if you get an insertion device that's tuned to have a single kind of event, so that energy change happens at only one kind of energy level, then you get monochromatic radiation off. And you can tune it by changing the magnets. You can tune the magnets to change the wavelength. So you can look at like different wavelengths with a synchrotron too, just by kind of turning a knob, more or less, kind of a big knob, but you can do it. So there's a lot of advantages to synchrotrons. I mean, 100,000 times flux is one of them, and then tunable, and then monochromatic and collimated. Like all the things you need are there. It's a package. The neutrons, you don't have that because you have this kind of explosion. There's no control over it really. All you can do is clean up the mess that came out. So you put it through a moderator, which is water, that absorbs some of the wavelengths of the neutrons, and then you can put it through a thing called a chopper. So this is a kind of inside of a chopper. So this thing's spinning pretty fast, and basically it's spinning at the speed of the neutrons flying down the tube. So they actually have, like, you can time them going down the tube. So if you move out far enough, the time of flight means that the high energy one's going to come first, and the low energy ones come later. So you can use time of flight. You can have a shutter that like opens and closes. You can get a spectrum at the other end just by the time there's a mass. The particles have mass. Like, you can't do this with X-rays because a photon doesn't have mass, but because these have mass, you use a shutter and you can separate the spectrum that comes off. So you can get monochromatic by a couple ways. One's by using this chopper, which spins and only will let through neutrons that are flying at a certain velocity. So it's a velocity selector chopper, right? And you can put a couple of these in the beam and you can select. And these are made out of like something that absorbs neutrons. So one thing about this kind of thing is that neutrons absorbed means the thing that's absorbing them becomes radioactive. Absorbing a neutron means the nucleus takes a neutron away from something else. When a nucleus gets more neutrons, it becomes radioactive. Like gold gets active as you stick your hand in the beam. Then you have a radioactive ring that you walk around with, right? So it's kind of a problem. You have to be careful about what you stick in the beam. Like some things are fine, like silica or silicon are good, but any kind of metal, basically, it could have a series, like iron has a half-life of like, I think 50 years or something. So if you stick iron in the beam, like you can, all right, the neutrons, because they aren't charged particles, they can fly right through anything. They can put a crankshaft into the beam, but the crankshaft is iron 55 when you take it out. So you can't put it in a car. You know, it's going to be like glowing in the dark, basically, right? So there's a lot of problems with radiation handling it properly with neutrons. Like they're perfectly safe. Like you can be totally blasted by neutrons and nothing really happens, like the neutron bomb, if you guys ever heard about that. It's kind of from the 90s or something, I guess, but they supposedly at Los Alamos, they invented a bomb that would just kill people and not kill buildings. It's called the neutron bomb. So just like zapped everything with neutrons. Have you guys ever heard of this? It exists, okay? We invented it. You know? So it is something that, it's one of the nasty things we've done, you know, but basically it's there. Anyway, so you can, neutrons, they'll kill you, I guess, if you get enough, but basically they don't really hurt you much. X-rays will give you cancer, like bone cancer, if you stick your hand in the beam. Neutrons, not much unless you have like a gold ring. Then because the gold ring gives off gamma rays, X-rays, the X-rays are what gets you, not the neutrons. So it's like the secondary things. So when you try to make devices like this, you have to be pretty careful about like what you make them out of, you know. So it absorbs neutrons. You don't want it to be, so boron is a good neutron absorber, and it doesn't have a long half-life. So basically you can make it out of boron, or you can dope plastic with boron, things like that. So the shielding all around a reactor is going to be polyethylene that's kind of pinkish because it's loaded with boron, borated polyethylene. So it's just like filled polyethylene with boron filling it. So you think, oh, I'd pile it up with lead. Lead's got 1,000-year half-life. So if you shield a neutron thing with lead, anyone that goes near that shielding is going to die, you know, or and it's also like toxic too. So lead has like multiple, it's like uranium, it's got multiple ways to kill you, you know, it's like so anyway, so there's a lot to this. Yeah.
So you're saying lead doesn't block the radiation?
Neutrons, no, it flies right through, but it activates it. It absorbs some of it. What it absorbs has 1,000-year half-life.
Oh, okay.
So I mean, yeah, so what you make is like a toxic material that's also radioactive. Yeah, so it's not, so say you're going to go to space. So this is a big issue. You're going to go to space, you're going to fly to Mars, okay? So you got a mixed radiation background, neutrons, positrons, all mixed radiation, gamma rays, super high energy X-rays, right? So what are you going to use? So X-rays, like lead is a normal thing that you're going to use to shield with, right? So yeah, I can just wear a lead suit and go into space. It'll be a little expensive, but I can do it. But the neutrons are going to turn the lead into a death suit. You know what I mean? So when you have these mixed radiation, there's no way to go to Mars safely. That's what I'm trying to say. And right now, when they go up into orbit or to the moon or something, they're basically in an aluminum can and there's no shielding, so you just get cancer. Like, right, so I mean, going to the moon is already like pretty dangerous. Like going to Mars is basically a death sentence, you know? And there's no shielding for it, and you're just out, and you go beyond the ionosphere of the Earth. It's nasty, right? So anyway, that said, so there's a lot of interest in the NASA and also in Department of Energy and like making mixed radiation shielding too. So people have been studying, like you can get a PhD in mixed radiation shielding if you want, you know, and it's basically you'll have a job forever because there's a lot of cases where you have mixed radiation. So anyway, the normal way to do neutron scattering is to build a nuclear reactor. Oak Ridge has a 60 megawatt nuclear reactor, which is huge. So Oak Ridge had a lot of reactors. Like they had the first graphite reactor. They've had, so basically the campus of Oak Ridge was kind of in the hills in Tennessee, kind of between this, within the Smoky Mountains, kind of. There's a Tennessee River Valley in the middle, so it's kind of off to the side of that. But anyway, they put it there because it was far enough from the coast so that the Germans couldn't bomb it in World War II. Like it was considered a safe place. All the sites like Los Alamos, Sandia, Oak Ridge, White Sands were all like located far from the coast, so that it would be far from German bombers, and submarines and stuff. Anyway, and also places where no one cared about like mixed radiation, things like that. Like no one cared about the Pueblo Indians in New Mexico and stuff, you know. So and also there were uranium mines out there, things like that. So there were reasons these things are where they are, but basically there's probably on the Oak Ridge campus is probably like 80 nuclear reactors, of which like 2 or 3 are running. You know, so it's like a nuclear reactor graveyard. You can actually go tour these things. Like you can do a nuclear reactor tour, you know, and see like the first graphite reactor and things like that. So anyway, so they have a 60 megawatt. So commercial reactors, that's basically a commercial nuclear power plant. It's like the lowest level of a commercial nuclear power plant. So it's a huge reactor. It was built just to make isotope californium, which is used for medical stuff. And in the time, and it's been around for 25 years, and it's only made like a gram of californium. You know, so yeah. Well, I mean, the first pile was at University of Chicago, and under the football stadium, and that was like 1945, I think. So it's been around a long time. And then after that, they decided that they'd do the Manhattan Project, and then they built a lot of reactors in the US. So Argonne National Lab outside Chicago, which is where the synchrotron is, they decided they'd have like these national labs to develop this stuff. So Argonne was like the peaceful use of nuclear, which would be like to blow up a mountain to make a road or something. And then Brookhaven was for biological, Brookhaven National Lab. Oak Ridge is a weapons lab. It was intended for enrichment of uranium. So the Y-12 plant is where they enrich all the uranium to make bombs, plutonium and stuff. It's still there. I mean, it's still doing it. And it's pretty funny because there's a golf course in Oak Ridge. It used to be a golf course and turned into a disc golf course. Okay. It's one of the best. I played disc golf. It's one of the best ones that I've ever seen, you know, because they have like sand traps and lakes. It's like a real golf course, you know. Anyway, there's a fence. It's right next to the Y-12 plant. So there's a fence with some barbed wire on it. And then basically you can throw your disc over the fence and guys come out with AK-47s and like whatever, you know, in a Jeep, you know, and like, what's this thing? Pretty funny. Anyway, so that's where anyway, so you'd think these places would be like the ultimate security, you know, but a bunch of the Plowshare Alliance people, they actually went through that golf course, cut a hole in the fence. They got all the way to the Y-12 plant where they're enriching uranium. They threw like fake blood onto it and sat down. And it was like 4 hours later that they realized that they were there. Like they could just walk in, you know. So I think the security has been beefed up. That was like 4 years ago, I think. But the security has kind of been beefed up since then. So anyway, this is also a place where, like Iran, they built a duplicate of the Iranian enrichment, the centrifuge that supposedly Iran has under a mountain somewhere. So, and then the Israelis made a software that like targets the control systems for that. and they infected every PC in the world with that software. So eventually it got to Iran, but they had developed that all at Oak Ridge at that Y12 plant. And they built a duplicate of the Iranian, whatever the tubes or something. Remember, they said that Iraq had these tubes or whatever, all that stuff. Anyway, somehow it's mixed in with that. But so a lot of weird stuff happens behind the gates here. But all right, so they have this giant reactor. It's called HIFER, high flex isotope reactor. And then Al Gore who was he was vice president for Clinton or something, right? But Al Gore was a big anti-nuclear guy, but he was from Tennessee, from East Tennessee, where Oak Ridge is. And then so they were going to build like a gigantic reactor, bigger than the HIFER, bigger than the 60 megawatt, like 200 megawatt or some gigantic thing. So best in the world, And it all went along. They were cutting the ground for it. And then someone told him it was a nuclear reactor. Okay. And then he said they cut the whole program. It was billions of dollars, Like literally this place, the SNS cost it cost $1 billion to build. It's a lot, so especially because the experiments are very slow. Like you can't run a lot of samples through it. Anyway, so when Gore found out about that, they decided to build what they call a spallation source, which is another way to get neutrons, but it's a lot messier. Like a nuclear reactor is nice and pretty clean. I mean, it's radioactive, but basically kind of know what you're getting, and the flux is constant. So you just have a single wavelength coming through. It's like your household X-ray diffraction setup. So basically you get a single wavelength out, everything's stable, and it runs for a long time, like forever, basically. Right, the lifetime of nuclear reactors maybe like 25 years, but basically with the extensions that they put on, they end up being 50 years. So they go way beyond their planned lifetime, which makes you wonder. The main problem with nuclear reactors is that steel rebarb in the concrete turns into iron 55 and it degrades as it's being activated. So you end up with a mess of crushed concrete, dust, powder that's super radioactive, and then the thing falls down, whatever. So there is a fixed lifetime, but they've managed to decide that it can go longer than that. Anyway, this place has a linear accelerator, which is over here, right? And that linear accelerator shoots over here, and then there's what they call a pile, quote unquote, a pile, which is a highly shielded kind of chunk of metal in the middle. And they blast whatever they get out of that pulse source into that pile, and then it irradiates off in all directions. So it's kind of like shooting a gun at something. I mean, so it's pulsing down this accelerator. And then actually the fence for Y12 goes right along here. So if you go out and jog around here, you get up to the Y12 fence, and then some guys in Jeeps come up. So the Y12 thing is all in this valley. Anyway, so it's just above that. I mean, they built a big research center to go with it. So like a nanomaterials center. There's some other centers here, and then there's that SNS facility. So this thing did cost $1 billion to build. So with this setup, you come in with a pulse and it makes neutrons, and you use time of flight to separate the spectrum. So every time there's a pulse, like 60 times a minute, or 60 times a second, I guess, then you get the whole spectrum coming out. So your computers have to collect a 2D pattern, and then like at 60 hertz, it's taking data, and then it's separating each time segment within that whatever 60th of a second into like the wavelengths. So your Q value changes. So you have a fixed angle that gives you Q, but it's 4 pi over lambda sine theta by 2. So 1 over lambda changes that with time. So you have to have a kind of a supercomputer to analyze the data to kind of break it up. The problem with it also is that the absorption spectrum depends on wavelength. So your absorption changes with each of those time slices too. So everything is like changing. So it's a complete mess, unless you're doing dynamic measurements, and then this is great because you have this time pulses of the thing, and you can do your dynamic. Like if you're doing T1, T2, you can get that's T1, T2 is already in your measurement, like it's built into it. Yeah. Yeah, there's a nuclear reaction that occurs in the pile when these charged particles fly into it. I don't really know. It's nuclear physics, but basically they send a charged particle into a chunk of metal, And then it glows, it gives off all kinds of radiation, but some of the radiation gives off as neutrons. Yeah. I think the accelerator is using electrons. The synchrotron sometimes uses antimatter, uses positrons, which how they get, it's hard to tell, but basically, yeah, so there's advantage to positrons because when an electron flies off, it's going to kind of give off radiation on its path, but a positron immediately combines with electrons and disappears. So once it leaks, it's gone. It's already history. It has to be in vacuum to exist. Once it leaves vacuum, it's done. But electrons still continue on their merry way, get absorbed in things and do stuff. Anyway, so that's kind of this place you can go to. You can write a proposal, you can go and use it. You can do neutron diffraction. Again, like if you have a crankshaft, you can stick it in the beam and get the crystal structure in the middle of the crankshaft, stuff like that, right? So, but so you can do small angle scattering with it. The nice thing is that hydrogen and deuterium have the largest difference in contrast of any materials on the periodic table. So basically, and they have identical chemical nature, right? So you can take a hydrogenous polymer and then make it with D2O instead of H2O, and you have a deuterated polymer, and you can mix like 1% deuterated polymer into a hydrogenous matrix or 1% hydrogenous and deuterated matrix. Then you can see a single chain in a melt, say under shear or whatever you want. So it allows you to light up a single chain, and it's exactly the same behavior as the hydrogenous chain. So there's a huge advantage to that. And the other thing is that, so hydrogen is going to be like your best material for neutron scattering. And like a lot of things are in water, like biology, and also fuel cells and batteries. Right, so there's a lot of battery work looking at, because it's so penetrating, because it's not charged, you can put a whole battery into the neutron thing. And you can do scattering or dynamics, whatever you want off it. So it's got some advantages. The disadvantage is that compared to a lab X-ray source, is about 1/10 of the flux. So a synchrotron, you have 100,000 times. There's 1,000,000 times difference between a synchrotron X-ray flux and the flux in this $1 billion neutron place. You can literally count the neutrons that are coming out. So it's like almost nothing. So it's basically like a really, it's good if you're going to you have some planned out experiment. You say like, I want to run 10 samples. Well, that's going to take you a week and a half. There's a lot of time to go eat pizza and play disc golf, when you do neutrons. With X-rays, it's 24 hours a day, and you got to be shuffling samples in all the time because they're running off at like 20 milliseconds a sample. So you literally have to have racks of hundreds of samples, and you're shuffling them in every hour, right? So it's a lot different kind of atmosphere. So one is like a sweatshop, and the other one is like a country club. So and the cost is about equivalent too. Like the cost per hour on this thing is going to be on the order of like $50,000, and on the synchrotron it's going to be like $1,000. So the cost is much higher. So anyways, nonetheless, so also this becomes like a space race of science almost. So everyone in the world wants to have the best neutron facility. So mostly we're like head to head with Europe and Japan, right? And China doesn't have this stuff. China has like one kind of junky spallation source like this in the southern part of China. Korea doesn't have any. So Japan, Europe, and us, and Australia has one that's not great. So basically it's a kind of a space race between us and Europe mostly. And Japan's a player in it too. Japan's really likes nuclear stuff for some reason, even though they had the atom bomb blow up there and everything. But somehow I guess we convinced them that like it was a great thing to have nuclear power on earthquake faults with tsunamis, But they more or less agreed up until recently. So anyway, so if you look at you can do the same trick as you do with X-rays and light. You shoot the beam in and you pick out at some angle, you have cues, you have a size scale that you're looking at, this whole thing about reflecting. So you're kind of doing exactly all the stuff that you did with X-rays and light, you do with this, right? But this is kind of the inelastic part of it. So you can't do the thing about speckle pattern that you do with XPCS and dynamic light scattering. So you have to go back to the old days when you took the light beam and shot it into the sample, and then you looked at the the wavelength distribution, the energy distribution of what came out. So it comes in with one wavelength, it comes out with that wavelength, but there's also some side wavelengths that have to do with the interaction of the radiation with the particle. The particle's moving, so it's a Doppler effect. Particle re-radiates the same wavelength. So it comes in and excites the electrons at a certain frequency, and then they're going to re-radiate at exactly that frequency, so the same wavelength, unless it's moving away from you and it's like the train whistle going away, or if it's coming to you, you get a higher pitch. There's a Doppler effect, and that leads to the spreading of the. So half of them are coming towards you, half are going away from you, so you get this bell-shaped curve, right? So that's called quasi-elastic information. It's got to do with the dynamics of the particles. And then there's also inelastic events, which are like spectroscopy. So in spectroscopy, like fluorescence, it absorbs a certain wavelength and it emits a different wavelength because of the electron transitions. So nuclei can have transitions like that too. And you can get peaks, spectral peaks that have to do with whatever's going on with that. So basically we're like interested in this dynamics part, which is kind of the quasi-elastic. So it's called quasi-elastic neutron scattering. So that comes out as QUEENS, QUENS, right? So versus X, everything has to have an acronym. But anyway, so you get this bell-shaped curve, and it's got to do with that velocity profile. Anyway, so what can you do with it? Anything with water in it. It's kind of like number one candidates, like biology. So he'll talk about membranes. So he's like Nichols is looking at. I mean, membranes are important to a lot of things. Like for one thing, fuel cells and batteries have like membranes in them, right? But basically, human cells and any kind of biological system. He's mostly interested in the biological transfer of things in membranes and looking at the dynamics of water, basically, in those systems. These are some slides from a guy that was doing Queens at Oak Ridge, looking at diffusion. Not sure what else, but basically kind of how you break apart the patterns. There's the main elastic, this is called the elastic peak, like the scattering peak. And there's this inelastic broadening of the peak. And then to get different energy ranges within that, there's a bunch of instruments. So at that one place at SNS, they have like 6 different instruments that are looking at different Q ranges. So it's like Q, these are the instruments, this is the energy. So each of them can access a certain energy distribution, like breadth of that peak. Then each of them is measuring kind of a different Q. So if you're doing diffraction, it's at high Q. So whatever diffractometers, and then scattering will be at lower Q. And anyway, and they all have different, like this neutron backscatter, which is a diffraction thing, is literally, there's a wall like the size of this room, and the entire walls of the room are detectors. Like, so it's pretty weird to see. So it's a gigantic room full of walls of the detectors. So you come in with your sample here, and then backscatters neutrons like that. And again, you get like 1 or 2 neutrons. So you have these, anyway, it's expensive. If you look at it, it's pretty fancy. Yeah. So at lower Q, you get Q's inverse size, inverse angstrom, right? So large things are down here. Large things move slower. I think that's the main thing. Like a big bell has a lower frequency. Small bells have high frequency. So high speed, small things, low speed, big things. And then the XPCS is going to be, well, it's going to be looking at a Q range in here between 1 and 0.1, maybe to 0.01. And then, but it's looking at very low frequencies on the second time, so it's basically very low energy things, like just diffusion of particles and things. It's much, so you can break up the whole world into a dynamic space if you want to. I mean, you can kind of say where everything fits in. So they're trying to map out. Anyway, there's a lot of people that have some idea for a machine with choppers and this and that. Like you can use the magnetic. So neutrons also have because when the nucleus. Let's see, what is it that spins? I guess the neutrons in the nucleus spin, and they develop a magnetic field somehow in that. So that's how NMR works. Like NMR is going to be controlling the magnetic field of precession of the magnetic field in a nucleus. Anyway, so neutrons are kind of looking at the same thing. So you can spin flips. So you can have the neutrons coming in with a certain direction. They can flip their spin by putting a magnet on it within this S&S thing. So it's kind of like an NMR measurement. They do spin flips. You can do that also in this. You can watch how long it takes for it to come back up using analyzer magnetic, almost like polarizers for light. So use magnetic fields like polarizers in light. Like if you put cross polars on, some of this birefringent will show up because it's got a 45-degree angle orientation to the thing. So it shows up between cross. So the same way you can do cross magnetic fields and neutrons and look at the dynamics of how long it takes something to flip over back into something, you know. So everyone has their pet way to do this. The chopper thing's one way, the magnetic field thing's another way. So they all get, so each of these instruments costs probably $100 million or some huge amount of money to build, some enormous amount of money. So this is a big money pit, actually, if you look at it that way. You know, like all the research money for NSF, like maybe this one place is sucking up almost that same amount of money. Not that that's a lot of money. Like NSF gets less money than Israel gets for military in the US. I mean, if you look at it that way. So the money is kind of funny, you know. So it's partly they give money to this because they say nuclear and they think it's a bomb. So then it's easy to fund it, you know, because you say, oh, nuclear, yeah, that's okay. So it's a little weird, you know, how the money flows, but this is a huge pit for money in a sense. Like Elon Musk probably should go down to Oak Ridge at some point, take a look at it seriously. But there is good science that comes out of it, and it's driven a lot of unique, like the understanding of the tube model for polymers, the reptation model. That's all the experimental evidence comes from this stuff for it. So that's kind of important in understanding how you extrude polyethylene, I guess. So depending on how important that is to you, I guess. Anyway, so this is a study on POS. So POS is a sesquioxane, so silica, SiO2, in a cage structure, kind of like buckyballs almost. They can stick, because it's ionic on the surface, you can stick things onto it. And that was thought to solve the world's problems at some point, but never actually, I don't think there's any product that ever came from that. That was originally invented kind of in the 2000s. There was the Air Force put a lot of money into POS. And then, anyway, I'm not sure anything ever, I never heard of any product that came from POS. No. But it's easy to make, but basically, I think silica is already doing quite a job. It's cheap, pretty cheap, so this is a little bit more expensive. But this study was just looking at the kind of mean square displacement, means the water molecules attaching to this. It's like saying how that changes with temperatures as a transition. And then, you know, there's tons of things. So let's see, I didn't put the papers up that I had for this week, but like if you, the thing is, like if you look up XPCS, I did this, you know, to find some papers. And then you find like, yeah, there's 2 or 3 papers from this year on XPCS. If you look up Queens and polymers, so restrict it down. That's without restricting it down. So actually XPCS is literally like this year, there's 3 papers, right? And if you look up Queens for this year, there's like 30 or 40 papers. So that's a narrow, it isn't like a huge, like 1,000 papers, but it's a lot more than XPCS. You know, so it makes you wonder, like if, it makes you kind of wonder, that said, like, I think in a sense, there's a lot more potential to, let's see. So I got these already lined up for this week, but I guess I just have a couple of these. But anyway, there are a couple. Let me just do that. No, that. What do I have here? So this is one of them from this year. Oops, right. So it's this PIN-PAM, the stuff that phase separates, kind of like PDMS that I showed you. Phase separates in water at kind of like body temperature. So it's used for biomedical drug delivery, and they surface grafted onto, and they're just looking at how, so the Germans are doing a lot of this. So this Jülich, Germany, this Garching's in Munich. So Jülich used to have a nuclear reactor. So all the brains in Germany are in Jülich, but they closed them. Actually, Germany decided to close all their nuclear reactors, power and research. They had 3 research reactors, which had the smartest people in the world at them, and they just shut them down. Meanwhile, France, which loves nuclear power, has like expanded their nuclear research reactors. So but the German guys are still stuck in Jülich, which doesn't have a reactor anymore. And Berlin also had a reactor, so basically those places both shut down. And then Munich has a spallation source, this Garching, Germany. So it's kind of like a mixture of lost people wandering around the neutron world, German guys in France, and it's kind of bad that the research things got tied up with the power things. But anyway, there's some guy at Florida doing stuff in this too. But just looking at PinnyPam, and then how the water interacts with it, and you can see they have the same thing. And then there seems to be what people are doing now. I'm not sure if Nichols would talk about. They convert that spectrum, that kind of energy, kind of scattering intensity versus energy for one Q value, into susceptibility, which you can fit with just Gaussian peaks. So you can, the susceptibility makes this curve, this featureless curve, look like it has features, basically. And you get that by dividing by the Bose factor, which is like the energy distribution. I'll talk about that on Friday, I guess. But anyway, so basically you can get this and you just fit it with Gaussians and figure out which kinds of water are in there, and that within the PinnyPam, and how it changes with temperature or whatever you want to do. Kind of look there. I think they're looking near that body temperature phase separation thing. So that's kind of interesting. And then there's a couple of Nature papers. So the XPCS, I haven't seen any Nature papers, so this is like, and there's a lot on membrane transport. So there's a Nature papers on membrane transport, but the XPCS is only a small part of it. So I'm not sure I'll do that one. It's totally membrane and a little bit of XPCS. So it's maybe not enough XPCS. These guys are looking at P.PSS is a conductive polymer kind of used for sensors and plastic electronic components. So this actually has industrial application now. They're looking at, it's water sensitive, so they're looking at the water sensitivity. And again, and it's a German group too, I think, right? Yeah, so these guys are kind of the same, similar group, like Jülich and place in Munich. And then they do the same thing, and then they convert it to this susceptibility curve where they can fit the peaks to it to figure out like what's the composition of water, how does the water attack this material because it's water sensitive, and how you maybe prevent it, So anyway, that's like a couple of it. There's like more papers on that. Like, so basically it's a pretty rich area for publications, and seems to have some interest. You can get the diffusion coefficient of water through a membrane as a function of pore size type thing, that kind of stuff. All right, so that's that thing. Then I thought that would take like 5 minutes, but anyway, it's stuff. It's kind of fun to talk about, I guess, a little bit, but it's interesting. All these things are going on. You don't know about it, They kind of keep it a little bit secret. And it's framed in a languages, so it excludes people. So language almost becomes a wall, and they like it that way because maybe they don't want too much inspection about the $1 billion they spent on this thing or something, or what. It's kind of hard to tell exactly. Oh, they do try to advertise it, but it still seems like science tends to wall things off, like try to keep a little cabal of people that are working on it. And anyway, I think so the notes just go through that business, and then there's something about, because we did dynamic, like how to raise gyration. So we already had this, I think, in one of the homeworks, but the RG by RH ratio. So you'll see that in a lot of biology where they don't know what the thing is. So they can measure RG by X-ray scattering, and RH by viscosity measurement or dynamic light scattering. They can get the ratio of the two. And you can see, like, for a polymer, RG is much larger than RH. More or less, you can think of it that the polymer kind of could go through the fluid as if it was like a straight line, so that it's almost like the diameter of the polymer is the drag coefficient. right? So it's got a lower drag coefficient than it would have if you took the structure, said like, I'm gonna get the mean squared distance through it. It's gonna be larger. So the thing that has like asymmetry, like a polymer, you're probably gonna get a big Rg to Rh ratio. And so polymers above 1 is the number you want to shoot for. Anything above 1 is going to be polymer. And anything below 1 is kind of something like you can think of as a sphere. So it's going through dendrimers where you branch, kind of degree of branching, and you find out it acts like a polymer, and then it transitions into a solid thing by the Rg to Rh ratio. And the coil to globule transitions, another thing people have looked at, like, so you have Rg, you have Rh, and then you do Rg/Rh, you can see it's above 1, goes below 1. So you have the coil and then the globule. And there's numbers that people have affixed. You can calculate the numbers, but basically that's the kind of thing you see. And then biologists will look at this and say, it first makes a compact form. This would be like in protein foldings, you say it makes a globule like a compact form. And then when it becomes an active form, it's larger than it was, it's more expanded. To kind of think of Rg/Rh as like an expansion ratio. So you can say this is a globule to native state transition. So you go coil to globule, so molten globules in biology, and then it becomes a native state protein that's larger. So this isn't a protein, but this is actually PNPM, the same thing they're doing with this. So you can see that's a popular material, polyinisopropyl acrylamide, because it kind of looks like a protein. The structure, it's not an amino acid, but it's got all the same atoms in it. So it's got an amine and a hydroxyl that can hydrogen bond, so it acts like a protein, even though it isn't. Anyway, so you can do this with a protein. You can do it with this kind of more model system, I guess. So that's one thing. That's just kind of a note in here, but you'll see that. Like this, I don't have amino acid here, but it kind of looks like the same structure as this, except this is in the main chain of the amino acid. So you can vinyl polymerize this, by something like raft polymerization if you want, make monodisperse PNPM, and then it acts like a protein kind of. So it's popular. It's really popular for surface grafting and things. Anyway, that business, that's kind of that. Any comments on that stuff? Or yeah.
Is the higher Rg to Rh just a more flexible thing, or?
Yeah, it means it's more, I guess you can think of it, it's more open or something like that. Yeah, so if it's expanded coil, you should get a bigger Rg to Rh than for a theta coil, and then collapsed coil is below 1. It'll be like some number like 0.7, 0.75 or something, I guess. So the exact numbers people worry about, people spend a lot of time worrying about it, but if the system's polydisperse, then Rg is just looking at the largest things. So yeah, it's a larger number because you're looking at the boulders on the beach. So basically there's a little bit of a fixing on this thing because nothing is going to be totally monodispersed. So if you look, it depends what you have to be careful about how you throw the things around because they're averages and what moment is the average. And a harmonic mean's weighted towards the small things because 1 over a small number is a big number. So if you average the 1 overs, you end up with the small ones are dominating. So Rh should be smaller than Rg by that argument, So anyway, but Rh gets larger than Rg if it's a 3D sphere, because Rh for a solid object for a sphere is the radius of it. That's the definition of Rh is the equivalent spherical diameter of the thing that has the same drag coefficient. Then Rg is smaller because it's going to be like weighting the material. It's going to be smaller than the radius because you're weighting all the stuff in it. So that means it ends up at 0.75. But so anyway, so it's kind of interesting to look at that. But again, like there's a lot of twists to it. People just throw it around like it's just a fact that's obvious, Let's see. So yeah, I guess I can wait to do the other stuff. Like the next thing to do, kind of I think the last formal stuff to do is go through this kind of transitions in the coil. So do that like probably next week, I guess. It's called the blob model. So, but there's a lot of different blobs. We've already seen like the coil collapse had a blob thing to it. And then you can think of the persistence length, the Kuhn length as a blob kind of. So there's other blobs. There's also electrostatic blob. So there's like, I have a table of the 5 blobs, but there's actually more than that. Every time you look at it, you can think of another thing as a blob. So there's a tensile, thermal, concentration, Kuhn length, collapsed coil. Then there's also an electrostatic blob. So basically, it's just how you have scaling transitions within the coil that accommodates something you do to it, which is unique to polymers. So I'll talk about that next Monday or something, I guess. Well, Nichols will be here. Sorry, Nichols wasn't here. Then Nichols will be here on Wednesday, and it'll also be like a mandatory thing. So I'll put another thing on the grade thing, and then Friday I'll go through the homework on one of those papers and on quasi-elastic queens. So then that's about it. Any other comments or anything? All right, let me quit there. Just for close.